All right, let's take a look at the squeeze theorem. We're going to use that squeeze theorem to evaluate a couple of limits, but we'll also take a look at a couple of other special limits and evaluate them in another way. So what is the squeeze theorem? It's also known as the sandwich theorem or the pinch theorem. But the squeeze theorem says that if f of x is in between g of x and h of x for all x on an open interval containing a, except maybe at a itself, then if the limit as x approaches a of g of x and h of x are both L, then so is the limit of f as x approaches a. Now that's a lot. So let's kind of look over this picture and go over the theorem piece by piece. First of all, it says that a couple of conditions have to happen in order for the squeeze theorem to hold. First of all, f of x has to be in between g and h over the entire interval, except maybe at one specific point. So if we look at our picture, what we're talking about is f of x is this curve in the middle here, and it stays in between h and g over its entire span. Now, there is a little bit of an exception here that it says potentially f maybe doesn't exist at a itself, and that would be okay because we're looking at a limit. Remember, with a limit, it's all about our expectation as we get there, not what actually happens as we get there. All right? So that's the first condition, is that f has to be in between those two over some open interval. Next, we have to have this condition that the limits of g and h approach the same thing. Right? And that's where the squeezing part comes in, is that even though g of x is below f of x and below h of x over that entire span, they do come together right at this point in the middle. And that not necessarily that those functions are defined at that point, but their limits are, that we have that expectation that whether I'm talking about g or h, the limit is the same. Then, since f of x is in between those two, that means its limit has to squeeze right in the middle of those as well. But both of those limits are L, which means f's limit is also L. So how might you see this on an AP exam? For all x on the interval from -3 to 8, negative x squared minus 2x plus 5 is less than or equal to f of x, which is less than or equal to absolute value of x squared plus 1. And we want to take a look at the limit as x approaches 1 of f of x. Now, we don't know what f of x is. We just know that it's in between these two. So take a look at the limit as x approaches 1 of our first function here, of negative x squared minus 2x plus 5. Now that's a quadratic, which means it's nice and smooth and continuous over its entire domain. It also means that to evaluate this limit, all we have to do is substitute 1 in for x. And that'll give us a value of 2. Now, this alone does not mean that the limit of f of x as x approaches 1 is also 2. All right? We know that f is in between these two functions, and I know the limit of the first function, but we also have to show that the limit of the second function is the same. So let's take a look at the limit as x approaches 1 of absolute value x squared plus 1. Well, x squared plus 1 is continuous, smooth, over its entire domain. Absolute value just makes everything positive, which it was going to be positive anyway. So we can just use direct substitution. And absolute value of 1 squared plus 1 is also 2. Right? Since f of x is in between those two functions and their limits are equal, that's going to mean that the limit as x approaches 1 of f of x would also have to be 2. So how about the limit as theta approaches 0 of sine theta over theta? All right, well, obviously, if we use direct substitution, we'd get 0 in the denominator and it all falls apart. But we can use the squeeze theorem to evaluate this limit. To help me get through this problem, I'm going to use this diagram. It's a unit circle, and on the unit circle, that would mean the radius is 1. And so we would have this smaller triangle where, if you remember, for any point on the unit circle, the x-coordinate is cosine and the y-coordinate is sine. And if we look at the larger triangle, since it's on a unit circle, its base is going to be 1, and opposite over adjacent is tangent. That's why that height is tangent. Now, why I bring this up is that if we look at the areas of these two triangles, obviously the triangle with the height of sine is going to be smaller than the triangle with the height of tangent. And the area of this entire sector is going to be in between both of them. So what I'm saying is the area of big triangle is greater than the area of the sector and also greater than the area of the small triangle. So let's go back and take a look at the big triangle. Right. Area is going to be 1/2 base times height. So that's going to be tangent of theta over 2. Next, we want to find the area of the sector. We start with the area of the entire circle, which is pi r squared. Radius is 1, so area of the entire circle is just pi. And then we're only going to take a portion of it. And that portion is whatever the angle is out of 2 pi. So obviously, when this simplifies, the 2 pi's will cancel, and we're just left with theta over 2. Now, when it comes to the small triangle, I really don't want to look at the small triangle that we used initially. I actually want to look at this smaller triangle. Now, the reason I want to use this triangle is its area is easier to find, and its area is still smaller than the sector. All right, so the area of this triangle, 1/2 base times height, is going to be half of 1 times sine, so sine of theta over 2. Now that my inequality is set up, I don't really need the diagram anymore. Next, I'm going to do a little bit of math magic. I'm going to take the reciprocal of all 3 fractions. So we'll have 2 over the tangent, and 2 over theta, and 2 over sine of theta. But the thing is that if I take the reciprocal of everything, then what was big is now small, and what was small is now big. So it switches all of the inequalities that we have. Next thing I'm going to do is multiply all 3 of these fractions by sine of theta over 2. And at 0, sine of theta is positive. So sine of theta over 2 is positive, so we don't have to worry about turning inequalities around or anything. But our first fraction, our first expression there, sine theta over 2 times 2 over tangent is going to simplify into cosine. And in the middle, our 2's cancel, and we have that expression that we want, sine theta over theta. And on the right side, the 2's cancel and the sines cancel, so that fraction simplifies to 1. Now I have my expression, sine theta over theta, is in between 2 functions. That's going to kind of signal to me that we kind of want to use Squeeze theorem. So to do that, we take a look at the limits as theta approaches 0. First of all, of cosine theta. Cosine is continuous, so we can use direct substitution. Cosine of 0, and the cosine of 0 is 1. That's not enough. We also have to take a look at the other side and verify that the limit as theta approaches 0 of 1, well, that is also 1. So since sine of theta over theta is in between cosine and 1 as x approaches, or as theta approaches 0, then that would mean that the limit as theta approaches 0 of sine theta over theta is also 1. Now, obviously, that's a lot, and I wouldn't really expect you to think of all of that on your own, but it is an example of how we can use the squeeze theorem in order to help us find the limit of something that is otherwise pretty tricky to do algebraically. Here's another one that looks like it's pretty tricky to do algebraically, the limit as theta approaches 0 of tangent theta over theta. And it's really not as bad as it looks, because when we're dealing with tangent, turn it into sines and cosines. So we'll have sine of theta over cosine theta all over theta. Now, just rearranging that, we're looking at the limit as theta approaches 0, and we can call that sine theta over theta times 1 over cosine theta. Evaluating those limits, we know what that limit is now. That's going to be 1. And as x approaches 0 of 1 over cosine, well, cosine is going to be 1 as well. So this entire fraction will simplify to just 1. Here we have another function. The limit is theta approaches 0 of 1 minus cosine theta over theta. Of course, you could use squeeze theorem for this one as well. I'm not going to. I just wanted to use this as a reminder, really. By now we have a handful of ways that we can evaluate limits. Squeeze theorem is one of them. So is direct substitution. But also we have tables and graphs. And if we were just to graph this function in radian mode and take a look at its limit as theta approaches 0 from the left or from the right, sure looks like they both approach the same number, that being 0. And the reason I bring these functions up is they are going to be very helpful for us when we're looking at the definition of the derivative later on. This function, 1 minus cosine theta over theta, as well as sine theta over theta. You should take some time and memorize the values of both of those limits. If you can't have them memorized, probably graph them and take a look.